So in this second part of section 6.3, dealing with random variables, we're dealing here with geometric random variables. The difference between geometric random variables and binomial random variables, the main difference is the set number of trials. So for binomial, we had a set number of trials predetermined before we even began, shooting baskets or whatever the situation is. Here, we don't have a preset. What we're going to do is we're going to keep going until we make a basket, and then we'll stop. So the random variable isn't how many baskets we make, but on which try do we first achieve success. So on which trial number do we make a basket? All right, and so that's the value the random variable takes on in these cases. So the first thing we're going to do is something called the lucky day game. And so what this looks at is, a hypothetical sort of situation here. Let's pretend that we have 10 homework problems for homework tonight. And then I want to know if, well, maybe you'll want to play a game in to help choose how many problems you have. So you can either have 10 homework problems, or maybe we could play this game. And so the game goes as the following. So I'm going to randomly select a student from class, and then that student will choose a day of the week, Monday, Tuesday, whatever. And then I'm going to get the computer to randomly generate a day of the week. And if the person chosen randomly chooses that correct day, then that's considered success. And so if we do that and the first person guesses correctly, then we'll have one homework problem due. If the first person is not correct, then we go to a second person. We randomly choose another person, and that person guesses. And if they guess correct, then that means we were successful on the second attempt, and in which case we have two homework problems. And so this will continue until someone guesses correctly. So for example, it might be the 12th person. Might take 12 people before we guess correctly, and in which case you would have 12 homework problems. Okay, so we are going to now look at my Excel spreadsheet sort of program that I've created. It has a class list. Now, if we were live, I would be doing this in the classroom, and I would have your names in here. But since this video is being watched by all my classes, I'm just using a class list from a couple years ago. And so you can see if I calculate, if I click on this button up here to calculate now, it randomly generates one of my students' names. On this slide, if I go on this sheet, if I go to another worksheet, I click on the tab down below for day of the week. The same time that those names were changing, the day of the week is changing as well. You can see every time I click on the button, a day of the week changes. All right, so what I would do is I would go, actually let me delete these. I have some stuff in here from using this before. Let me get rid of those. All right, and so what we're going to do is play this game. And so what I'm going to do is randomly, so I'm going to have a calculate, I would have the computer randomly generate a student's name. And then if we were in class, I would say, okay, Elliot, pick a day of the week. And so then, sorry, my Amazon speaker is talking to me from the other side of the room. All right. So let's say I would calculate, I would have it calculate a name, randomly generate a name, and it would be Izzy. And so I would say, okay, Izzy, name a day of the week. And so Izzy would say Saturday. And then I would switch over to the day, and I would say, oh, nope, the day was Wednesday. So Izzy did not get it correctly. So let's make a tally mark. I'm keeping track of how many students it took to correctly guess the day of the week, the same as the computer generated. So I calculate another student, Lucy. Okay, Lucy, what day of the week do you pick? And Lucy says, well, I pick Saturday. So we go over and it's Sunday. So and now it's taken 2. All right, so switch back over to the class list, generate a new student, Marcel. So then we would say, okay, Marcel, pick a day of the week. Marcel would say Friday.
and then we say, oh, nope, it was Tuesday. So our count, remember, we're counting how many attempts it takes to get a success. Here, success is the correct day of the week. We go over to Noah. Now we ask Noah, Noah, what day would you pick? Noah says, I pick Friday. So we click, and nope, it is Wednesday. And so we make another tick mark, and we're going to continue this until someone guesses correctly. We go to the next. All right, so we go to Lucy. Lucy, what day do you pick? And Lucy says, oh, I pick Friday. And so Friday it is. So in this particular attempt, it took us 5 attempts to guess correctly. All right, let's do this again. I want to play a couple times. So 5 was one outcome. Let's pick another student, Hugo. All right, so we ask Hugo, Hugo, what day of the week do you pick? He says Monday. And so Monday it was. So we won on the first attempt in this case. All right, so let's go to a third game. Go back to our class list. Calculate somebody. All right, Izzy again. Izzy, what day of the week do you pick? And she, of course, says Friday. And so I go, and it was Friday. All right, so we won twice in a row on the first attempt. All right, and let's play one last time. Marcel, what day of the week? Friday, he says, and it was Friday. So we see in this case we won. We won after one attempt 3 times, right? So not unrealistic, not unheard of. We went from 5 down to 1 and 1 and 1. All right, so not unheard of, but so the idea is, are those ones typical, or is that just kind of a fluke that we got 3 wins on the first attempt? And so we're going to investigate this in our slides. The last time I ran this, I think I got answers for the 4 games that I ran. I got something like 3, 2, 1, and 13. So we got a rather large one on one attempt. In this case, we got 3 1s and a 5. That's pretty good. So if we were playing this game, and if you all agreed to have played this game, and I agreed to let you pick how many homework problems you had based on this game, then you would have 5 homework problems, or you'd have 1, or you'd have, if you were unlucky enough to be in the one class that got 13. So you can see you can get anything from 1, and 13 is not uncommon. I think I played this one year with kids, and we had as much as 15 or 16 tries before we got one that was correct. Okay.
So if we look and see, we look at the games that we just played, we had, if you're given the choice of 4 homework problems in playing the game, you would probably just do the 4 homework problems, or maybe you'd play the game, because we got our game results were 3, 2, and 1. So that means if we had looked at those, if we had counted those games towards our homework count, we would have had 3, 2, or 1 homework problem. So maybe you would even play after 4, but we also had a game that had 13 in it. So 4 sounds pretty good compared to that 13 we might have gotten. And even 10 maybe sounds good. 15 starts sounding like maybe you wouldn't play the game if you would definitely play the game if I said 15 homework problems or lucky day. You probably all would say, yeah, let's play the game, because we're bound to get fewer than 15. Some people might choose to play with, if you had 4, some might choose to play if you had 10. 15 probably sounds like we're more likely going to win the game before the 15th attempt at guessing the day of the week. So I guess the question is, what's the break even? How many, if we played this game again, 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 on average, how many tries do you think it would take on average to guess correctly? And so you might think about what that would be. All of this deals with a geometric setting. So in a binomial, we had a fixed number of trials. Here, our trials end once we get success. So we don't have a fixed number. So we have 2 outcomes again, success and failure. each trial should be independent of the others. And then in this case, we're going to record the number of trials it takes for our first success. And then the probability of each trial of success for each trial should be the same. And so the acronym we got here is BRRS. I know they're kind of lame acronyms. Last one was BINS, where you had a fixed number. Here we record the number, so it's R, so BRRS, which, I mean, you know, is not a very good acronym, admittedly. All right, so in the geometric setting, we define the random variable, in this case, let's call it y, to be the numbers of trials needed to get the first success. So what's interesting here is we can list a lot of trials, but we can't list all of them because we don't know how many trials. In theory, we wouldn't expect it to take 1,000,000, but in theory it could, right? The probability that it would take 1,000,000 guesses before we got the correct day of the week is pretty low, right? It's not very likely it would take us that long. Indeed, most of ours were below 5, right? Most of them was 3, a 2, and a 1, and then we got one that was 13. So, but we can't list how many it's going to take. So you notice the possible values of y are 1, 2, 3, and then we do a ... because we just don't know what the probability. We don't know how many it will ultimately take. In theory, that list would go on forever. But again, the probability that it takes a really high number before success typically is pretty low. All right, and so this is a geometric random variable. And so like binomial random variables, it is important to be able to distinguish between the ones that are geometric, the ones that are not geometric, or maybe binomial. So let's look at some examples. So number 1, shuffle a deck of cards, turn over the top card, put the card back in the deck, and shuffle again. Repeat until an ace is observed. So this is similar to what the example we did when we were doing with binomials. Binomial random variables. Is this one geometric? And sure enough, yeah, it is. The possible values are 1, 2, 3, 4. So we don't know how many it will take. So we don't know. We can't list all of the possible values. We still think of this as discrete, even though technically can't list all of the values here. We do still kind of think of this as, it's not a continuous. You can't have a fraction. It's got to be an integer. All right, so this is a geometric random variable. What about the next one? Choose 5 students at random from your class without replacement. Let y be 0, 1, 2, 3, or 5 who are over 6 feet tall. This sounds like one of the examples that we did with binomial. This is neither binomial. We talked about how binomial without replacement, the independence rule is violated, and so that's necessary for both geometric and binomial. This would be more geometric if I were to pick people at random, and then how many people would I have to pick before I got a 6 foot tall person. That would be more geometric, but it would still be not geometric because of the not replacement thing here. All right, number 3, roll a die, a fair die, 100 times. Let W equal the number of 5s you roll. All right, so is this geometric, binomial, or neither? All right, this one is binomial because of the set number of trials. We're not going to stop once we get a 5. We're going to keep rolling 100 times and then just count the number of 5. So that is definitely a binomial random variable. All right, number 4, Bob places 1 chip on a corner bet in a roulette. And then for each consecutive spin of the wheel until he wins. So Z is going to be, could be 1, could be 2, could be 3. This is definitely geometric. Also notice that with geometrics, you can never have 0. You can't win with 0 tries. In binomial, you can have 0 wins in the trial set. But for geometric, you never start at 0, you always start at 1. And so yeah, this is going to be the same. The probability is the same every time. It's independent, not a set number. We're going to keep going until we get success. And we have either we win or we lose. So all 4 situations are satisfied here. All right, so the geometric probability formula, lucky day game. So let's go revisit that lucky day game for a minute. Random variable of interest in this game, y, is the number of guesses it takes to correctly match the day of the week. What's the probability the first student guesses correctly? The second and the third, and we're going to use that to develop our formula here. So probably the first person guesses correctly, well, they have 1 in a 7 chance, or about 14%. Now, what about the probability the second person guesses correctly? Now, you might say, oh, well, isn't that just one out of 7? Yes, but think about what has to happen for the second person to guess correctly. That means the first person has to guess incorrectly. So in other words, not just what's the probability the second person guesses, but that it takes a second person before we get the first guess, and before we get the first guess correct. So that would be the probability the first person guesses incorrectly is 3 out of 7. Probably the second person guesses correctly is 1 out of 7, or about 12%. Now, what about the probability of 3? So remember, probability that it takes the third person means the first two guess incorrectly, and then the third person guesses correctly. Can we think about what the formula would look like? So remember that first thing, 6/7, that's the probability of failure. 1/7 is the probability of success. So how many failures do we need? Well, it's 1 less than the number of tries it took before we got success. So we have the probability of failure, 1 minus p, raised to the k minus 1. And then there's only one success, so it's p raised to the 1 power, or just p, because we stop after we get our first success. So a little bit simpler formula than what we saw when we were dealing with the binomial. All right, we have ways of doing this in our calculator as well, as you probably guessed. So if it's a geometric probability command, if it's the probability that the random variable y equals a particular value, then we simply use geomet PDF. That's for an individual value, probability of an individual value. You have to put in the p value and the k value are the inputs for that one. And then less than or equal to k. So the probability that y takes on a value of k or something less than that, that's the CDF. Just like the binomial CDF, it calculates for a particular value and everything below it. So we have to use the complement rule if we want to go in the values above a certain value. Okay, the probability of getting something bigger than that. So let's say that in the Lucky Day game, using our TI-84 calculators, let's calculate the probability that the class will have 5 homework problems. That means the 5th person guessed correctly. All right, so the probability that y equals 5 is a geomet PDF, because we're looking for a particular value, not a range. The p-value is 1 out of 7, and you can type that in your calculator. You don't have to figure out what the decimal equivalent of 1/7 is, which I think we said was like something like 14%. So we can just type 1 divided by 7 right into the argument for our command. All right, and so that gives us about 7.7%. And using your calculator again, calculate the probability that the class will have less than 8 homework problems. So less than 8 homework problems. So that means if sometimes it's helpful to sort of write out all the possibilities and say, okay, less than 8, that would be these. And so what number, we're going to use the CDF here, the geomet CDF. And the value that goes in is the highest value of the part that we want to calculate. So our geomet CDF should have 7 in it. So 1/7 for the probability, comma 7. And so that's going to give us the probability of it being 7, 6, 5, 4, 3, 2, or 1 added up. All right, and so that's about 66% chance. All right, so table below shows part of the probability distribution of y. So let's show that. And then the missing values, we can calculate those using our calculator. And you can see here, we could certainly create a histogram. Now, this histogram is sort of asymptotic. The probability that it would take more than 25 guesses for our lucky day game is pretty low, but it's not zero. So we can't really, just use our idea that these are discrete random variables and add them all up, because it goes on forever. Okay. What shape does it have? Well, this is definitely skewed right. Regardless of what the p-value is, the further out you go, the less likely it's going to take 25 or 100 guesses to guess correctly. All right. How fast you get to that zero is going to depend on what the p-value is, but ultimately it's going to be skewed right for sure. All right, so where is the center of this thing? Well, as you expect, that kind of makes sense that you would take generally 7 guesses on average to guess correctly. All right, you'd expect in the long term it to take 7 guesses because there's 1 in 7th chance. So indeed, that's not a coincidence. It's going to be the reciprocal of our probability. The standard deviation, we're not going to ask you to calculate here, but we will ask you to interpret it. And it's a pretty large standard deviation. That's why you noticed when we were playing the Lucky Day game, we got quite a variety of answers. We got some guesses on the first try, some it took up to 13 tries. So it kind of makes sense if you think about it. One of our answers was about 6 away from 7, so it took us 13. So we would expect there to be quite a bit of variety in the outcomes if we played this game several times. So how do we interpret it? So if the class played Lucky Day game many times, the number of homework problems the students would receive typically differs from the mean of 7 by about 6.5. All right, and so the mean really is just 1 over p. So the probability of guessing correctly on any individual guess is 1 out of 7. So we would expect it to take about 7 tries on average if we played this game many, many times. All right, so replacement versus not replacement in the geometric random variable. So suppose the tech supplier inspects a simple random sample, size 10, of a shipment of 1,000 flash drives. So we have 1,000 flash drives, a box of 1,000 flash drives, and we take and we sample 10 of them and we test to see whether those 10 work or not. Also, let's assume unrealistically that we know that 2% of the flash drives are defective. All right, let X be the number of defective flash drives in our simple random sample. All right, so is this a binomial setting? Let's calculate the probability that the first 9 flash drives work and that the 10th flash drive is the first one to fail. All right, so this is sort of a geometric setting here in this case. So the probability the first one it works is there's 980 of them. So I pick one out. There's 980 that work. 22% are failures. So out of 1,000, and then you notice that I'm not replacing it, right? I tested that one, it works. Okay, now let's go to the next one. I randomly sample one. There's 979 left, right? And so as a result, the probabilities are changing a little bit. And if we looked at the decimals, you say they're changing a little bit, not that much. The last one, of course, is the probability that the last one is fails. And so we get this kind of a value. Now, what if we used our formula to calculate this? We can see that we're assuming that the probability is the same every time, assuming sort of independence. Using our independence rule, you could see that out to the 4th decimal place, that the answers are really the same. And so even though we know the probabilities are changing every time, they're not changing by that much. The population is so large and our sample size is not so big. It's not bigger than 10%. It's really only 1% of the population. And so we're okay when we don't sample too many. The probability is changing a little bit every time because I take it out and I don't replace it. These first couple are actually look like they don't change at all. They do, but out to past 4 decimal places, they're not changing. So you can see it's really not a big issue, this not replacement thing. All right, so your homework for this section, you notice that there are a couple that have parts that require your 3 steps, so make sure that you're doing those as 3 steps.